All right, welcome to lesson number 9, dealing with reasons for the seasons. In this lab, we are basically taking a look at what causes the seasons to occur, and we're going to also talk a little bit about the notes that go with it and try to tie the two together so you have a good understanding of what actually causes our seasons. To start with, I took this picture from a group that did a nice job of setting it up today. Basically, they have a thermometer that is at a 45-degree angle. They have a thermometer that is at a 90-degree angle. They have a thermometer that is at a 0-degree angle. And this light was simulating the sun. And so the sun is obviously coming down and striking the 0 degree. It's coming across to strike the 90, and it is hitting the thermometer at a 45-degree angle. So let's take a little look at what we were trying to accomplish with this. If we start by drawing our sun, here is our sun, and we're adding to it, give it a little face. The sun's light is obviously traveling through different forms of electromagnetic waves. And our Earth is always in a position to be moving. And so if I draw Earth right here, the Earth has different parts to it. There is basically the top part, which is going to be called the poles. There's a North Pole and a South Pole. And then going across the middle, we have that imaginary line, which is called the equator. And then obviously this part here is the northern hemisphere. And this part down here is the southern hemisphere. And so the idea of the lab was to try to get you to see what would happen if our sunlight was having to travel and hit at a 90-degree angle the North Pole, at a 45-degree angle the North and South Pole, or I'm sorry, the northern and northern hemisphere and the southern hemisphere, and then at 0 degrees being the equator. So we kind of turn this into 90 degrees, this one into 45 degrees, this one into 0 degrees, this one into 45 degrees, and then this one into 90 degrees again. And so those were the different angles of the light. Now, as you did the experiment, I'm sure that you started to discover that the 0 degree one had the highest temp that you would have seen. The 45 probably was a close second, so second place for 45, and then 90 probably wasn't too far, but it finished in third place in terms of temperature increase. And so if you think about that, if we go back to our image that we had drawn here, it probably makes the most sense to us, the fact that the light is just having to come down and to travel straight across and hit this one. We would expect that it would get the most sunlight. So this area is getting the most direct sunlight. This one, on the other hand, is not getting the most direct sunlight, because what's happening is that the light has to come down and over to be able to strike it, while this one is getting a good amount too. And so if we start to apply that into our questions that we had, the first question said, in this experiment, what was the independent variable? So the IV. If you remember, our independent variable is the one thing that's being changed. So our independent variable was the angles of the thermometers, and our dV, which is how did we measure the angles of the thermometers. So our dependent variable is depending on the independent variable. The thing that was actually how we measured it was based on temperature. So every minute for 10 minutes we recorded the actual temperature. And the control group was most likely the fact that the light, same size wattage, was used, the fact that you had used textbooks to set it up, and the fact that you were, most of you, probably using the same type of thermometer. And I'm sure there are other types of control groups. Remember, control groups are what did you keep the same. So the independent variable, what is it that you changed out of the experiment, keeping everything the same. Dependent variable is how did we measure the independent variable. And then the control group is what are the things that we were set up and kept the same. Question number 2 said, based on your data, at which angle did the temperature increase the most? Correct answer would have been 0 degrees Celsius. Again, we talked about it. If this is our light, it is shining down at a direct angle to hit the 0 degrees Celsius one, so that would have been the most. At which angle did it get the least? The correct answer would have been 90 degrees. And again, the reason why is the fact that the sunlight has to come down. If this is where a thermometer was, it has to come down and bend. The angle of light is being bent. So that was the question, the answer for number 2. Number 3, which part of Earth's surface does each thermometer represent? We kind of went through that when we were drawing the Earth, so we'll quickly go through that one together. So here is the Earth. Remember that our sunlight was drawn from right there. And so this one right up here represented the North Pole, so it was 90 degrees was the poles. The 0 degrees was the equator, and the 45 degrees is the hemispheres. That's what that represented. And then why is air at the North Pole very cold in the summertime? And the main reason for that is, we can answer it right up here, is the fact that you have bent angles of light. And so what that means is that anytime that you bend the light, it is not going to have the most direct effect, and so it's not going to heat up as fast. It's the reason why the equator is one of the warmest spots on the world, on the Earth, because of the fact that it's receiving the most direct sunlight. These ones are receiving indirect sunlight. So the fact that it strikes the poles in itself is amazing, but also it's the fact that you're striking the poles at a bent angle versus striking it directly. So that's the answer to the last question. Let's take a look at some of the notes and try to tie this back in together. To start with, we need to look at what our overall topic is, which is astronomy. And astronomy, by definition, is going to be the study of the moon, stars, and other objects in space. And astronomy is something that people have always been interested in. It's just been something that has not been easy to study. And so basically in ancient times, people would look up into the sky and they would notice that the fact that the sun and the moon were always seemed to be moving. And obviously what's happening is the fact that the Earth is moving around the sun, but people thought for a long time that things were moving around us, and it's actually the fact that we're moving. And there's two ways that we are able to move, two major ways that we are able to move through space. And the first one is basically rotation. We are constantly rotating. The second one is revolutions. Those are the two ways that we're able to move through space. And we're going to look at each one of those a little bit closer here. So let's take a look at rotation. You guys are probably already familiar with the fact that the Earth is rotating, and it is what causes our day and night. So if this is our Earth, let's get a picture up here. If this is our Earth, the fact that it is turning causes us to have day and night. And obviously it turns so that way the east or in hemisphere, the eastern part of the United States receives the sunlight first, and then the western part. And so that's why when we did the opener question of where is the sunlight going to appear first, in New York City or in Miami, and the answer was New York City because of the fact that it's further east. It takes 24 hours, a little less than 24 hours, but we use 24 hours to complete one rotation, and we call that a day and a night. Now, understand that going through the Earth, there is an imaginary line that is called the axis. It's basically a line that goes from the North Pole, cuts all the way through the Earth out the South Pole. And we talk about it as there's this actual line that's there, but it's not. And what it does is it helps us to envision the tilt of the Earth, but also the rotation that's occurring. A revolution, on the other hand, is what causes a year. 1 year, which is equal to 365 days. And to be more specific, there's actually 364.25 days that are in a year. And these 0.25, or basically 1/4, is what actually causes a leap year. So every 4th year, we end up having an extra day because of the fact that it's 0.25 plus 0.25 plus 0.25 plus 0.25, which actually equals out to be 1 whole, so it would be 4 out of 4, which is equal to 1 extra day. So 1 year. Now, what you have to understand about this is the fact that if this is our sun, and our Earth is going to be located right here, understand that the Earth is revolving around the sun. Okay, it's going around the sun. And so when it makes one complete revolution all the way around, we call that a year. This path that it's on, which is drawn absolutely horrible, is called an orbit. And it is not just, it's not like a perfect circle. It's actually called an elongated circle, which means that it's going to have a little bit of a belly to it. It's going to go out farther, and so it's not a perfect circle. And it's what allows for the Earth to orbit or go around or revolve around the sun, which causes us to have our full year. And so rotation, revolution, that's how we basically look at the Earth. And so to also put into what we had done in our class, let's talk a little bit about the fact that we have our seasons. Our seasons are caused by, let's take our sun and draw it right here, give it some rays of sunlight. So this is the sun. Let's draw our Earth in a couple of different positions. The first position that we can refer to, we'll say that this is going to be March. And March is associated with spring. And if we draw our axis going through it, it is actually pretty much straight, going right through the middle. There's no tilt to it on a March day that we call the March equinox. And the equinox means that if we're talking about the rays of sunlight, they are going to be striking equal amounts at the northern hemisphere, equal amounts at the southern hemisphere. The most direct sunlight is occurring at the equator. So the equinox means that there is the most direct sunlight striking the equator, where the northern and southern hemisphere are actually getting indirect sunlight, but they're getting equal amounts of it. And so what happens is over the course of the year, as the Earth continues to move into different positions, it's going to change the axis point. So if we move to the next season for us, and obviously it's different in the southern hemisphere, the axis point is going to actually cause us to point kind of like this forward. Now what's happening is that the sun is going to be striking the area of the northern hemisphere more than the southern hemisphere. This one is going to have more bent angles. So again, it comes back to that bent angle of light where it's more at a 90-degree angle, forming the right angle a little bit closer there, where now in the northern hemisphere it's getting more of the direct sunlight. And so because of this, it allows for us to have warmer temperatures. And so this would be more of our month of June. And it's called a solstice, where basically one part of the hemisphere is getting more sunlight than the other part. And so the equator still is getting a fair amount of it, but now the northern hemisphere is getting more sunlight than, more direct sunlight than the southern hemisphere. And so we see warmer temperatures, which is what causes our summer. This was spring, now we have summer. And as the Earth continues to rotate, so if we continue to draw the fact that it's moving around the sun, we come to another point in time, again, where the axis line is almost going up and down, and the sunlight is traveling more directly again. Oops, wrong color. It is traveling a little bit more directly at the northern and also again at the southern hemisphere, but the equator is getting the most direct sunlight. So again, it's almost identical to the month of March, with the exception that now we are moving into a different time period, which is going to be the month of September. And September is obviously the beginning of fall. And again, we use that word equinox. Equinox being the fact that the equator is getting the most direct sunlight, bent light in the northern and southern hemisphere. So again, notice how the axis line is almost straight up and down. Same thing with the month of March. Here it was bent. So the Earth continues to not only rotate, which gives us our days and nights, but it's also in the process of rotating to a point where we can see that there is again another angle that is bent. This time the axis line is coming through with a bend to it. And obviously I've probably drawn these a little bit more dramatic than they actually are, but I wanted to at least give you the effect that now the southern hemisphere is getting most of the direct light along with the equator, where now we have that bent light, which means that we are going to experience winter. And so this happens in the month of December. So December is the start of winter. And so we also refer to this as a solstice, in which we have usually in December comes the shortest day of the year. I believe it's somewhere around December 21st or 22nd. The longest day of the year for us is in June, again somewhere in that 21st, 22nd range. And again, this whole thing will happen again. And this whole process is a revolution, and it's what actually causes the days. It actually is what causes the years, and as the Earth continues to rotate, it's what causes the days. So the lab showed us basically a way for us to see how bending light actually causes temperature changes. And since there's temperature changes, it's going to cause the seasons to be different. So if we were to apply what we had just learned, most of the time what we see is the fact that in the month of March, we're at more of what you would consider to be a 45-degree angle. Same thing with the month of September. This is more of our 45. The month of June, for us in the northern hemisphere, we're not at zero, but we're closer to zero because of the fact that we're getting more direct sunlight, and clearly it's not zero, the equator is, like we had talked about. And then this one is also a situation where we're at more of a 90-degree angle where we're getting bent sunlight. And so kind of fits into what we were talking about, but keep in mind these axis points are a little bit more over dramatic than what they actually would be in the real world. Hope this helps, and talk to you later.